The final ANOVA analysis we're learning about is called the two-way ANOVA. Sometimes it's also referred to as the two-factor ANOVA or a factorial ANOVA. A two-way ANOVA is what you'll use when you're looking at two independent variables at the same time. Up to this point, we've only looked at one independent variable at a time. But there are some situations where you might think that there are two variables that impact a dependent variable simultaneously. So for one example, you might ask a question, does room temperature and or humidity affect test scores? In this situation, there are two independent variables. The first is the room temperature in red, and we'll see here that there are three groups within that variable, a 70-degree group, an 80-degree group, and a 90-degree group. The second variable we have is humidity, and if you look down on the left side of the chart, you'll see that there's a low humidity group and a high humidity group. I've simply set these up into this grid because it helps me understand the two variables and how they're going to eventually start working together throughout this test. A second example might be, does a drug treatment work differently for different genders? In this situation, the first variable we're looking at is drug treatment, and then purple you can see that we have a drug group and a no drug group. And then the second independent variable is gender, and you can see in the blue on the side that we have a men and women group, so again a two-group variable. Both of these would require a two-way ANOVA because we're looking at two independent variables. The terminology that we use, though, instead of saying two independent variables, is that what we're actually looking for is two main effects, one main effect for each of the independent variables. So looking back at our example of does a drug treatment work differently for different genders, we're asking, is there a main effect of the drug treatment? And also, is there a main effect of gender? You can see in the chart below I've actually put in some mean values just to kind of give us a sense of what would happen in the test. For example, with the drug treatment groups, the drug versus no drug group, you can see that both of those groups might score a 30, meaning probably if you ran the statistic you wouldn't find any significant F value. And then also simultaneously the output is going to tell us what's going on with genders in the blue, and if we had a mean for men of 25 and a mean for women of 35, that would probably lead us to a significant result. So here we're asking about two different main effects, the main effect of drug treatment and the main effect of gender, and we're going to get different answers for each one. In addition to the two main effects, there's also going to be one interaction. And an interaction is it can be thought of as the effect of one variable depending on the other variable. So if we go back to our example of drug treatments and genders, it's possible that whether or not the drug works depends on what gender you are. So I've added additional means in orange in the boxes that would be representative of, for example, the upper left orange box would be men who received the drug. The upper right orange box would be men who did not receive the drug. The lower left orange box would be women who received the drug, and the lower right box would be women who did not receive the drug. So there's now four combinations of these two independent variables, and each would have a mean, and we can see that what happens for men might actually be different than what happens for women. So in the men group, the score was higher for the men who took the drug than the men who did not take the drug. But the opposite is actually true for women, where the women who took the drug had a lower score than the women who did not take the drug. What that means is how effective the drug is depends on whether you're a man or a woman, and that is an interaction. Now, the interaction is actually the most important part of the two-way ANOVA. If you get a significant interaction, it trumps or is more important than either of the main effects, even if you get significant main effects. The reason for that is because once you have a significant interaction, if it's the case that one variable depends on the other variable, then the main effects are too simple of questions to be looking at anymore, and they become less important. As has been the case with all of the ANOVAs we've run thus far, you do have to conduct post-hoc tests under certain conditions, follow-up tests, to find out where there's significant differences if the F value comes back as being significant. So if you have no significant main effects and no significant interactions, then of course you don't have to run any post-hoc tests. However, if there are significant main effects, either 1 or 2, but there's not a significant interaction, then you would use the Tukey's HSD for the significant main effects in the exact same way we've been doing thus far. Things start to get a little bit different here, though, because if you have a significant interaction, whether there's a significant main effect or not, you're going to be having to do a post-hoc test for just the interaction and not the main effects anymore, because remember, the main effects are not important if there's a significant interaction. And the way that you'll do this is through graphing the interaction, and that's something that we'll be looking at next week, so don't worry too much about it now. So to kind of overview the layout of what you're going to need to do in a two-way ANOVA, there is going to be a requirement for each main effect and an interaction. So for each of these three things, the main effect 1, the main effect 2, and the interaction, you need to write a separate set of hypotheses. So that means you're going to have a null and an alternative for the main effect 1, a null and alternative for the main effect 2, and then a null and alternative for the interaction. 6 hypotheses overall, essentially. You also are going to have to run an F-test in PSPP for all 3. Fortunately, you just do the work once and it gives you 3 F-tests in the output. And then for each of these F-tests, you need to report your results. You're going to have an F-value statement for each, and then you're also, if necessary, going to have a post-hoc follow-up for each. So this leads us to approximately 3 times as much work as we've been doing in any of the other tests, but that's because it allows us to ask much more complex questions. So for a concrete example of this, if we go back to our question of does a drug treatment work differently for different genders, and we use looking sort of at the same data that we had been, what this means is that for the first main effect, which was drug treatment, you would have to write a null and alternative hypothesis. You would have to look to the PSPP output for the F, and then based on that, write a results report, including the report of the F value and, if needed, any post-hoc follow-up. For the second main effect of gender, you would do the exact same thing. You would write a null and alternative hypothesis. You would look at the F value in the PSPP output, and then you would write the results. And then for the interaction, here we have a drug treatment by gender interaction, and often you see this little X used in the place of the by, so drug treatment by gender interaction. You also will be writing a null and alternative hypothesis, looking to the output in PSPP, and writing up the results report. And details about where to look in the PSPP output and writing up the results can be found with the attachments in the folder from this week and a little bit more in next week.